In the phase in optics, we have diverse meaning of phase. So in real optics, we know the light is electromagnetic wave. So we characterize complex amplitude, we get phase. Phase can be used as a ruler to measure precise measurements, for example, for CR and industrial samples. The phase is also a very important component for incurrent correlation imaging for synthetic action or passive imaging for far distant objects. And another very important issue is 3D optic metrology. The main topics of this talk is we use fringe pattern. So it's very classic fringe pattern. So in photography, so we project on the surface of the pattern. So we can establish correspondence between two stereo camera. So we can convert this phase information into the height or 3D depth of the image. So this is the main topic of my talk here. And we know our world is 3D, but if we take photo by using our camera or our smartphone, so actually 3D then is projected onto the surface of the object. So in this case, so we can the third dimension Z along the optic axis Z has been lost. So how do you cover the third dimension is pretty important. And optic technology, optical 3D sensing, is most typical and widely used 3D sensing to recover the lost third dimension. So we have a lot of optic 3D sensing technology. For example, we have photometric stereo vision, time of flight, shape from modus, and spectral light. This is my topic of my talk. And based on the structural pattern we project onto the surface of object, we can divide into the fringe projection technology and the spectral projection technology. With fringe, we have projection performance. We project spectral pattern, we have the spectral projection. The basic idea of fringe projection is quite simple. Our beams, we have two eyes. Actually, we call it baseline. Is the distance between our two eyes is 16 millimeters. So we have two eyes, we capture the scene with two slightly different perspectives. We have left image from our left eye, right image, and by combining these two images and match synthesized in our brain, we get this disparity line. Because they slightly change along our this baseline direction, and this disparity band actually is proportional to the depth. So the main text for the 3D sensing based on stereo vision is the image correlation. But you can see here some mathematics. I think this is the most complicated slide in my talk. Is the depth information Z in object to the distance to the baseline here is inverse proportional to the disparity B, which is the distance between two matching points in the two sphere image. For example, we have 1 point P. Here we kept two images. Because of disparity, we have these 2 points on the two images. Here at the R, we can see the depth Z inverse proportional to this distance. This means if the object is very far from our camera, so actually two images of most of the scene, there's very little disparity. So you can see very little disparity corresponding to very large data. So the most important test is how to find the corresponding point between your camera, your matching pixel. But the situation becomes very complicated if the object contains no information on the surface. For example, if you want to measure this white wall, so we take left image and right image, we get this kind of tuning. With most people, most of the pixel is 255. So if we have 1 point A on the left camera, suppose you find a candidate matching point on the right camera, it's quite challenging because the ambiguity, same pixel, but we have almost many candidates have the same value, pixel value. So how to solve this ambiguity? So we can use structured light. If we project additional structured light on the surface of the object, we can re-examine the pixel A, the neighborhood pixel. You can see such a random pattern here, and we search the neighborhood pixel with these candidates. We can see the only correct candidate point C have the similar structure. This actually the spectral pattern become an artificial feature, which establishes unique correspondence between these two images. This is why we use structured light instead of passive stereo vision. So we can how to do the 3D sensing for this full field view. So we do, you can see, we do a slide window operation and to measure the similarity. The highest similarity corresponding to the correct matching disparity. So we can convert these steps into 3D, high 3D information of the sample. So this technology has been actually go into our daily life I think in 2010, and it's the Kinect as an accessory of Xbox 360. You can see it's game player invented by Microsoft. And you can see here the Kinect, when we play games, it projects some dots, infrared dots. Our eyes cannot perceive this infrared dot, but the infrared camera can capture such kind of image. And with this image, we get 3D depth of our player. So we can play games without using any game computer. It can recognize our posture gesture. And this one, I think everybody here is know this one. Because the miniaturized version of the Kinect becomes this 3D sensor of using by our iPhone. And when you unlock your iPhone, it actually projects a lot of dots onto your surface of the face. And we cover the 3D surface. We can actually do the face recognition, 3D face recognition. And in China, you see a lot of vending machine. You can pay by just simply scan your face. And we have developed such a 3D sensor. So, for example, we have UnionPay in China, very famous bank payment, and we actually have them to make such kind of miniaturized 3D sensor. Here's the raw data, and here's the depth information you cover by using this very miniaturized device. And you can see we can implement everything onto a laptop. So without using a computer, we get rid of the computer, or we use it in real time. But the most important thing is you can see the resolution and the depth. You can see resolution pretty poor. The Z precision is very low for this technology because we need to do sliding window operation. So resolution is a big problem. How to solve this problem? So we can turn to another kind of structure like we call it fringe projection topology. We project fringe onto the surface of the object. So we have so-called fringe projection topology. So the fringe pattern actually is has its roots in interferometry. We have two coherent beams. Before we can form such a fringe pattern, and we shift the optical path length of one beam, we can do phase shift, we can solve the phase. We borrow this idea and actually into the 3D sensing. So we have this kind of fringe projection topology. We project some pattern, sensory pattern on the surface of the object, and we do phase shifting. We solve the phase, we get a vector phase map. Minimum 3 patterns. We solve this based on this arctangent function is a standard equation for phase shifting. And the most important thing you can see here, the phase is wrapped to 2-pair range. So we have periodic ambiguities. So if we can remove this ambiguity, we get so-called phase unwrapping up, we get unambiguous phase. In this case, we can establish one-to-one correspondence between the project pixel and the camera pixel. Because we know phase specify the location of the periodic function. So we know the phase is high, that is in the middle of one centimeter. In this case, we can establish correspondence between point A and point C, corresponding same point on the surface of the object. So we can count the phase into the height of the object. So then we get 3D surface of just like the 2D image, if we want to capture 3D model of the object, we do a 360-degree and we just all these points call together, we get 3D model, complete 3D model of the object. Advantages, point by point measurement without any sliding window. This phase is pixel dependent, independent. We do it actually based on the temporal function. So, but this advantage is periodic function. You can see because the central pattern is periodic, this means if the object is oscillating, you can capture such kind of fringe pattern. You can see there are 5 fringe orders in the project coordinate. But in the camera space, you can see there are some fringe order missing between. So how to solve this fringe ambiguity? Because we can only solve the vector phase. How to get fringe order information? So we must use the temporal phase unwrapping approach, TPU. The basic idea is quite simple, straightforward. So we project additional group of fringe pattern. For example, we can project a unique fringe pattern, unique fringe pattern, and then solve the phase. There's no ambiguity. Then we project additional high fringe span. this has certain ambiguity. So we use it as a baseline to unwrap this. You can also, there are following methods you can choose, but at least you need two groups of fringe patterns. So this means if you want to build a high-speed 3D shape measurement system based on fringe projection, so you need to at least use two groups of sensitive patterns. One is unit frequency, no phase ambiguity. The whole field will only have one fringe. So do the after phase shaping, you get perfect this model. How to see it? So it says no 2-pi phase jumps. But this one we have several fringes, so we have some ambiguities. We use this as a guide to unwrap this one. It gets perfect high precision unambiguous phase measurements. That means we call this 3+3 phase shifting algorithm. So totally we need 6 patterns per 3D measurement. This naturally lead to the question that can the number of patterns be further reduced? Because actually for our 2D camera, we just take snapshots to get an image. But for 3D imaging, we have at least 6 patterns, 6 images. That means the temporal resolution has been reduced significantly. So this is a goal of my life, is to increase the high speed of 3D imaging by reducing the number of patterns per measurement. We have developed a lot of methods to reduce the number of patterns per measurement from 6 to 5, 4, 3, 2, 1. I'll just show you some examples. This work we have been done in about more than 10 years ago. You can see instead by using two groups of sensory patterns, we use one sine, one cosine, one increasing slope, one decreasing slope. Because the pattern is projected by using such kind of DLP projector. So it does not like the interferometry. So interferometry, we can only have the fringe pattern, but in this case, in fringe projection technology, we can project any kind of pattern you want. So you can see you can project such kind of increasing slope, decreasing slope. In this case, using these equations, you can see we get two groups of phase. We can do the temporal phase unambiguously by using these 4 patterns. But at that time, there's no DLP, no DLP, right? So we do a reverse engineering of a DLP projection. We're using an FPGA, so you can see. So we can actually do a very fast speed fringe projection at 316 hertz, and we realize 120 real-time 3D, 120 hertz real-time 3D image system that have no iPhone, and I think maybe the earliest 3D real-time 3D sensor, high precision 3D sensor over the world. So you can see here is the real-time 3D sensing of human body. Okay. Perhaps display on the computer. Because we realize the temporal phase unwrapping, so we can see the object can be very complicated. It contains several isolated objects. So by further reduce the number of particle measurements, we use additional camera. Based on the epipolar line, we can reject some false candidates. This means there's no need to project additional pattern. We can only use 3-step phase shifting algorithm, 3-step sensor pattern to cover the unambiguous phase. Based on this, we build a real-time color 3D imaging system. Here we use 3 monochrome camera and 1 color camera as a texture. We can realize real-time high precision 3D imaging at 15 fps with a depth precision of 4.5 micrometers. So this the 3D measurement precision is 1 to 2 magnitude higher than the iPhone. In 3D surface, we have this 3D color image, and we map to the point cloud of the geometry. And you can, if you want to build a 360-degree model, you just put your sample and rotate it in front of the system. You can see we can do real-time staging to build a 360-degree of a very complicated object in less than 1 minute. And we send this whole point cloud into a 3D printer. We can make the object very easily. And so far we achieved 3. So how to get the single shot method? It's nothing new. It's Takeda's method. If we project a very high frequency pattern onto a surface of object, and we do not do phase shifting because we have only one pattern, but we take Fourier transform. It's a very highly studied paper invented by Professor Misu Takeda. Do a Fourier transform, get a Fourier spectrum like this. We select plasma order, just the off-axis holography. So we get phase very elegantly. So we get phase, we get a 3D profile. But the most important thing is there's accuracy and ambiguity problem. So the phase obtained by Fourier transform is very low accuracy, and there's depth ambiguity. We need to know the fringe order. So this technology has been widely used, but only limited to the very smooth surface, like the surface of the drum and the surface of the artificial vehicle being. How to measure complicated objects is a very challenging issue. So based on this idea, we further improve the Fourier transform topology and develop the called micro Fourier transform topology and realize 3D measurement at 10,000 frames per second. So here is our system. Instead of using a fixed high-frequency pattern, we change the frequency. We change the wavelength of the fringe pattern slightly, and we create such kind of pattern sequence. And using high-speed camera, high-speed projector to project surface to the surface of object, you can see this is our projection sequence and the 20 kHz DLP projector, and we have high-speed camera. We capture the corresponding 2D image, and here you can see here is the rotating fan blades. The speed is about 2,000 rotations per minute. That means for 1 second, the fan rotates 13 more than 30 circles for 1 second. So if we use your iPhone, you can capture such kind of image. Even the speed is 100 FPS. But in our system, we can capture such a nice fringe patterns, and we can solve the phase and get the very nice unambiguous phase on contraction of the fan blades like this. And here we will achieve the 10 kilohertz high resolution 3D surface imaging like this. So based on this idea, we can capture very interesting thing. You can see here is the tool gun. It's not real gun. It's bullet shoots onto the plastic wall and jump back to in front of us. You can see here only less than this here is time. Here is the 3D frame. We can stop the time to see how the bullets rotating in the 3D space. You can see there are less than 100 milliseconds. We capture more than 3,000 frame 3D point cloud. And you can see we can also calculate the 3D trajectory of the bullets. We calculate the speed, instantaneous speed of the sample, and we can also capture this bullet triggered by a flying dart. You can see here these two rubbles overlapping in 2D, but actually they are separating in 3D because it's large depth separation. So you can see the balloon blowing up took place only in 3 milliseconds. We can recover the 3D surface very nicely by using this technology. So far is classic phase shifting, classic Fourier projection topology. We have written a review in 2018, and this paper has been cited for more than around 1,000 times. And for more detailed information, you can refer to this review article. And so far, we hope to achieve single shot 3D high-speed, high-resolution 3D imaging. But actually, we still cannot use FTP. We need to achieve patterns. But recent development, artificial intelligence, deep learning, inspire us to go further step. I think everybody here knows Google's DeepMind AlphaGo, and now we use ChatGPT every day. So it's kind of powerful tool for our daily work, daily life. And recently, the Sora, OpenAI, in the Sora, they can create video from text. For example, here is a paper birds flying through the forest. You can generate very cool 3D animations by using this artificial intelligence. So we must borrow this very nice idea and rapid development of artificial intelligence into the optical metrology. So we applied deep learning to analyze fringe pattern in 2019. And this is our first work, apply deep learning into fringe projection topology. We apply deep learning for fringe pattern analysis. I think the most critical issue in fringe projection is how to recover the phase from single fringe pattern. And Takeda's method means if we have a very large high frequency carrier, in this case, we take a Fourier transform, we can separate A and B cosine phi, because B cosine phi in the Fourier space we have two delta function, ideal delta function, two exponential term, and we do use a low pass filter, we can get this term, and we do active function, we can get the phase function. But actually, you know, the object contain very abrupt, very tiny details and abrupt jumps. In this case, we have sprinkles overlapping issues. So how to solve these issues is pretty challenging for single fringe pattern. But we can do this by using deep neural network. The first neural network, we use one single fringe pattern as an input, and we use this pattern to estimate the background image A like this, and then use the arctangent function to get the phase function phi. So this is kind of this work is very early, but it's a kind of physics inspired neural network. This you may wondering why we direct map the intensity I x y to the phase function phi. It's based on the end-to-end model. But the most important thing is here you can see the phase function contain very too many abrupt jumps. It's not very to follow by our conventional neural network. We do an arctangent function, we get a sine, cosine, because sine and cosine are continuous function. It's easy to be followed by neural network. In this case, we do an arctangent function to get the phase function. So here is based on the conventional phase shifting model to recover phase from single fringe pattern. And how to train the neural network, we use of the share of samples, because how to get the label for fringe projection topology is very easy, because we can use, for example, multi-step fishing algorithm to get the ideal phase by using a lot of fringe pattern. For example, in our research, we use 12-step fishing algorithm, and we remove the 11 fringe pattern and use left only one pattern to recover the phase of about 12-step fishing algorithm. You can see here is the result. Here is the input. Here is the output of the A, like this. You can see it removes the fringe pattern very nicely and get the background. And the second CNN2 gets the sine and cosine. And after the arctangent function, we get phase function phi here. And you can see compare with the conventional FDP and blended Fourier transform. Here the deep learning approach. It almost duplicates the 12-step fishing algorithm. But remember that we have only one fringe pattern as input, and this one use 12 phase shift patterns as an input. And another important issue is even the carrier frequency is low, you can see the Fourier transform method and the blended Fourier transform method get terrible results because the spectrum overlapping issue. But in this case, we use deep learning. We don't assume the fringe should be separate order in the frequency domain. So in this case, it also give you very nice results, even comparable to the 12-step fishing algorithm. And actually, this work is being reported by several academic and social media. And it can also be generous to imperfect fringe pattern. For example, we have some gamma, we have some saturation, we have some what we call it non-sinusoidal fringe pattern. So it's very challenging for conventional method. For example, we will cause some harmonics, some errors onto the surface of the object. But after we do the deep learning, it can remove this kind of articles. Very nice. And next, how to achieve single-shot 3D imaging. So we can actually re-implement all the idea of based on the conventional classical method by using deep learning, because deep learning is very powerful for solving the inverse problem. For example, we can compare the geometric constraint with deep learning without using any precise calibration procedure. For example, for the first neural network, we have two cameras. We have two patterns from different perspectives. And for the first neural network, we use this arctangent function. We get the two phase value. And second neural network, we estimate the fringe order. And we combine these two, we get the 3D data by just using one shot fringe pattern. But this conventionally we need to very precise geometric calibration. But in this case, we just put the sample here and we do the multi-frequency phase shifting algorithm to get the ground truth data. And then we can train the neural network very easily. And by combining these two neural networks, we get the 3D data without any ambiguity. Here you can see compared with results. You can see history. If the object is moving, we use multi-frequency phase shifting, at least 6 patterns per measurement. You can see the motion artifacts very severe, and deep learning approach, single shot. And this one is the ground truth. If the object does not move, here. You can see if the object is moving, you can see conversion method, motion artifacts, deep learning approach, no artifacts. And we can also combine the different color images. This we call the color multiplexing, using different color, different wavelengths. By using a color camera, so we can actually capture 3 different intent images by using one color camera. So here is idea proposed by Professor Zhang from Hebei Technology University of Technology. But you can see for conversion method is quite challenging because of spectrum, because the color leakage, color crosstalk of the color camera. But we can apply this approach to deep learning to do the color separation. You can see here is our recovered phase, because due to the crosstalk, the deep neural network not only recover the phase but also remove all the crosstalk. And how to train the neural network, we use single color image as a ground truth and do the 12-step phase shifting every as a label. You can see compared with conventional method, the measurement precision is significantly enhanced. And you can see by projecting one color image, we can also get high precision 3D profile system. And we can also do the frequency multiplexing. Here is a very elegant idea proposed by Misu Takeda. Just as in a conventional communication system, we can use frequency multiplexing. We superimpose 2 frequency patterns onto a C, one image, and do a Fourier transform. You can see, 2 harmonics. So we can do the bandpass filter to extract these 2 patterns. We have 2 phases, but actually it was terrible. You can see because at around the edge of the object, it has some frequency leakage issue. But we can use deep learning to do the decomposition very nicely. You can see here is the multiplex pattern, and we use 2 neural network. One is for phase demodulation. The second one is for phase unwrap. We can separate these 2 group patterns very nicely. Here is a channel neural network. You can see here is the 2 ground truths, and we add them together, we get a composite pattern. And after fringe demultiplexing, we get the phase. Here's the result. You can see by projecting this composite fringe pattern, and we can recover a very nice 3D model of the object. And finally, how to apply deep learning approach to our real-time system. So we are not just limited to public papers. We need to implement all this into a real system. So here is, you can see, here is our high precision color 3D imaging system. You can see we have 3, even though we reduce the number of patterns from 6 to 3, when we move, you can see some ripples of the hand. How to solve this issue? So we use the same hardware, but we do the deep learning. We change the software, but we keep the hardware unchanged. In this case, you can compare, because the deep neural network using only one single shot patterns. This one traditionally use 3-step fishing patterns. You can see when we move the object, you have some motion artifact inside. But this single shot approach is totally resistant to the motion artifacts. It's body-free reconstruction. Here is the ripple. The ripple because the phase shifting errors induced by the motion. Finally, is so far we achieve single shot 3D imaging. That means the 3D imaging speed is comparable to a traditional 2D image. But how to go one step further? We can, for example, the projector here, the DMD speed is very high. It can achieve 20 kHz. But for high-speed camera, it's very expensive. So usually the camera is at the level of 100 frames per second. But the DMD, we can achieve much higher speed. So we can do the multiplexing to include different information along the time axis into the frequency domain. And we can have this such kind of multiply spectrum. But how do you demodulate this spectrum? Quite challenging because we can see the certain overlap. But we can use deep learning to do the demultiplexing. We can achieve kilohertz 3D imaging with a conventional low speed around 100 fps camera. You can see here the relative temperature. You cannot see anything, but after we do a deep neural network, we can demultiplex this single pattern with different angles, and we can achieve 10 group of phase by using one multiplex fringe patterns. So we can see here is the contrast family. And we can further do the spatial super resolution. We can see for high-speed camera, the speed increase significantly with the reduce of the pixel resolution. This means if we can use very small pixel size, it can enhance the temporal resolution of the camera significantly. So we can use such a kind of low resolution image to do a super resolution to recover both the phase and enhance the spatial resolution. In this case, we can achieve 100,000 frames per second 3D sensing by using a conventional high-speed 2D camera. Finally, is the deep neural network is often treated as a black box. That means if we input one frame pattern, it can always give you a very nice phase reconstruction, very nice 3D model. But does this neural network method can provide correct or right answer? We don't know. But it's, for example, in computer graphics vision communities doesn't matter. But for the optical metrology, industrial applications, this issue may be critical to address this problem. So we think actually we propose a method so-called phase neural network. To along with the phase estimation, we obtain another very important quantity. We call it uncertainty of the phase reconstruction. That gives you some measure of the reconstruction error. For example, you can see because the recover phase from single frame pattern is quite challenging issue. But you can see here in the sample in the industrial part, it contains some screws. You can see screw thread here. It's like the frame pattern. If we capture one pattern like this, you project the additional pattern onto the surface, this kind of surface, it will create some real pattern like this. But the deep neural network never seen this before. It will create very terrible reconstruction like this, you can see. Because there are certain ambiguous. You cannot hear this kind of fringe structure belong to the object or belong to the pattern you project onto the surface of the object. But if we measure this use deep learning approach, it will create terrible results. For example, it will treat this as a maybe not good sample. But if we are 12 efficient and here measure it perfect. How to solve this problem? You can see, but in our phase neural network, if we show you on uncertainty map, you can see here this part with very high value. That means the deep neural network see, I don't believe this method, this result I create is correct. So this part is okay, this part may be incorrect. You can maybe resort to other conventional method to measure this part. So this gives us additional choice. We can use deep neural network, we can use AI to do metrology, but the AI may tell you, I don't believe the results is correct because actually we based on some prior knowledge, we based on some data, but sometimes it does not work. So we need to go back to the conventional approach. Okay, here is a conclusion of my talk. So classic fringe projection is a very established approach for measuring 3D surface of the sample, but it's very challenging to realize single shot, high resolution, high precision 3D shape measurements by combining deep learning approach with fringe projection or structured light. We can achieve high precision ion radius measurements and further push the fringe projection of metrology a further step to high precision real time and single shot method. And recently we published a review article in Light Science Application, and it has been cited for more than 360 times. And this is we can see. So here is a conventional fringe projection topology and optical metrology flow chart. But after using deep learning, and we make everything much simpler and elegant. And if we go to Google Scholar and search, for example, phase shifting, phase unwrapping, and in front of this term, we plus deep learning, you can at least find more than 5 papers so far. So that means I cannot see deep learning is the future of open metrology. But deep learning is now leading a paradigm shift from physics-based modeling to data-driven learning. I'd like to thank my students, colleagues, and collaborators. Anyway, thank you so much for your attention. Thank you. Happy to take any question.